any event, one of the things we do here, when we bought this company, basically had two components to it. One is an aerial camera they produced. Turns out this little company by the name of XL owned about 50% market share in the aerial camera business, the large-scale digital frame cameras. We happen to have our processing site, and they did a lot of their technical work in terms of processing the imagery that came off the cameras here in Boulder. So we kept both groups. One group, the camera business, was in Graz, Austria, and the processing guys were here in Boulder. This happens to be a little ghetto up and down the corridor between Digital Globe and Space Imaging, or in Longmont and Thornton, respectively. MapQuest is down the street in Denver, so we're here. Lockheed Martin's over in Greenwood Village or something like that. So this is a bit of a ghetto for people that are into photogrammetric processing. It's a pretty small industry as it goes. And we happen to also have a fairly large compute site out in Longmont. We have 8 acres across from Seagate, out on Nelson Road near the airport. We currently only have an acre of it populated, but that works out to, right now we're at 72 petabytes, and just yesterday we got delivery of another 60 petabytes, so we're going to be up to about 150 by September, and then we're going to add another 30 in December. So we currently have 20 aerial cameras flying, and we're moving to having 45 cars with a 54 megapixel sensor out there on the roads. If you came in today and you happen to see that big screen with all the little blue lines on it, what we actually do, we actually use Azure. Our cars communicate over a cell network up to Azure as to where they're going. When they're driving, you can actually click a button on that screen and you actually see where they're going. We call it the Pac-Man app, and we actually track where the cars are going, and you actually see Blinky or whomever going around. Man, somebody said, "Oh, you name them." I go, "No, you don't. You should. That's so stupid." So anyway, we're going. We'll add that. You'll see that next week. But we both fly and drive, and these are. I'm, by the way, notorious for not doing anything with the slides. I tell a completely separate story from what you see on the screen. So if you see something that catches your eye and want to ask, by all means do it. We also made a personal camera there for a while. We make it, we use it for a little bit, and we put it aside, it rots away. And so that's something we haven't really focused on seriously. And there's some examples. When you came in the door, you saw our camera number 2 system was sitting on that half of a car sitting in our lobby there. But now we're already up, we're on our second version after that already with the new 54 megapixel sensor. By that we mean every time we take an event, there's 9 cameras on it, and when you add it all up, it's that size, and we make a panorama out of it. And we take a picture about every 4 meters. I'm going to talk about just one of the programs that we've done, just to give you an idea of the kind of processing that we do and pushing around. So recently we had done a project in concert with Digital Globe. They sold our data. We put it up on big maps, which is we flew the entire United States and all of Western Europe, except the Northern Scandinavia countries, but all of Western Europe, at 1 foot resolution. So if you're a spy or into this stuff, what you care about when you go out to buy an aerial camera is, what's the resolution of 1 pixel on the ground? What's the area that it covers? And in an aerial camera, it's all a function of the height the plane flies. So we made a special camera. There's an example of it on the left. By the way, we do sell cameras. Anybody interested in a really high resolution camera, they're only about $750,000 a piece. Like I say, we have 70% market share, and that works out to about 30 cameras a year.
Does it fit on a mountain bike?
With big tires. Yeah. So a flight typically will bring in anywhere from 1 to 3 to 4 terabytes of data in one capture event. This particular camera system that we built special for this, which we did not sell, flew in 10,000 square kilometer units, which is a very, very high acquisition rate. Typical cost of acquisition, which is the high cost in this stuff, is about $40 a square kilometer. This camera could produce data at $5.50 a square kilometer. So it was very effective. And when the USGS did it, it took them a decade to fly the entire United States at 1 meter. We did it at 1 foot in a little less than 2 years. For a fraction of the $250 million that the government spent doing it. So, we are just about, this is an old picture, we've filled in most of all the area in Germany and northern Italy there and stuff. but we still have planes sitting on the ground. And the biggest part of our bill now is paying a pilot to sit and get drunk in Ireland every day, waiting for clear weather. We've been sitting there for 2.5 months, right? And so, we're starting to think the weather is clear, but he's not. But in any event, the impressive part about this camera is it captures an image every 3.6 seconds, and it's a 417 megabyte image, right? So we're sitting at the other end of a pit hose, right? When data is coming off of it.
Is that Area 51 in Canada?
Of course it is. Of course it is. Years ago, I did a project some of you might have heard of called Terra Server. It was one of the first websites. That's me. That's how I got into this whole thing. I was a database guy that said, how hard could it be to, take pictures and put it on there? If I'd have known round earth, flat monitor was hard, I'd have never done it. Right? But in any event, we had worked with a deal with the Russians, and we had this thing where if you see a famous place, we'll put it up. And it wasn't quite worded quite right. It was something worded as, if you'd like to see a famous place, tell us what it is. Well, I got inundated with email. And the number 2 requested place was Area 51. So we sent this little message off to our Russian buddies and say, any chance we can get Area 51? And it comes back, the exact mail message, in broken English. What you want it for? Look-alike dirt.
So what's your highest rate of refresh for imagery on a given area, and what's your lowest rate?
Lowest rate's never, because we haven't gone some places. There are some places that are never cloud-free. Burma, a lot of problem. Myanmar, isn't that what it's called now? Ecuador is a very tough place to
How about
fly.
in the United States often?
We'll fly, some places we fly almost every 18 months, but that's accidental, usually. Usually we pick up some things because we're off flying something else, we just take the pixels. Our intent was, with this program, to fly every 3 years on it. And rural areas, and you can see some lines, for those up close, you'll see what we call high-value areas. They were going to be at anywhere from 2 to 3 years. Like we're going to try to do New York every 2 years, as an example. Although, truthfully, you don't have to, because New York doesn't change very much. It's really high-growth areas that you want to fly frequently. But in any event, the other thing that happens is we have ADD here, where we get into other flying programs and go, ooh, shiny object, let's go do that instead, right? And I'll tell you a little bit more about what we're doing in that space. So we don't always achieve what we want because we see something else we want to do different on it. So, like every other business, a little bit about the camera. I probably won't read all that, but in and of itself, it's a supercomputer. It has 13 computers in it, which is one of the reasons why it costs what it does. A big chunk of memory will go into SSD drives. Now we can get data off it at 2.2 seconds, which is a very big deal. It's what is the fundamental function. Biggest problem we have with our latest camera is we can't fly it low enough and slow enough to capture the detail we want. And when we do this stuff, we call it orthoimagery. And between Apple doing 3D and Google doing all that, and one of the things they call it is almost orthopornography now, because literally, we're getting closer and closer and closer. You can see way more detail than you really want to. Today, we all have to blur faces when we do street side stuff. We're going to have to go to that in aerial processing on beaches. I'm not kidding. We're getting to that. So we're a little out of control in the race war for resolution. But a little bit of techno dweeby stuff here. One single picture is 9 kilometers and 6 kilometers on a side. We fly 18,000 feet above wherever the altitude is. So here we be up around 23,000 feet. And when we take the photo, we have 3 images actually come off of it. A very large grayscale image, it's low resolution. Color infrared, this happens to be Rome. Not a lot of greenery in Rome, so infrared. Green comes back red, blue comes back black. Really handy for finding vegetation and water is what it's really useful for. We use it in our processing. And then the natural color image, you can actually see people walking around the square. But obviously you can't identify them at 1 foot resolution per pixel. So processing is complicated. And we don't use Hadoop or MapReduce, but we have our own that we built. It was what I came here to do. I was into a large-scale server processing, was my background at Microsoft. And so we built our own graphing system, mostly because I could never figure out how to do key value pairs just an image. What's the key? What's the value? Right? You tell me, I'm open. What do you got? Right? Especially we don't know where it is yet. So we say, well, what's the location? No. Right? That's part of the processing we have to do, and we want to do in parallel. So in any event, part of it is my own limitation, not being able to figure out how to actually use it. But I thought I'd just show you some of the examples of, a couple quick examples of what the hard part is. That picture on the left is one 10,000 square kilometer collect. Right? You see it have this very distinctive different color in there. What do you think that caused that?
The sun.
Pardon me?
The sun.
The sun?
Like our clouds or...
No, we always do cloud-free, and there's the least amount of haze that we can do. Turns out it was cloudy over that spot. They got the left part and the right part, and then they got caught in rain. It rained, they got up the next day, right, after the rain, and the earth reflects totally differently with moisture in it than it does without. Another gentleman, I was talking to another gentleman early here when we first did this program, one of the other things that came back, every time a plane lands, we say, there's always a data surprise in there for us, somewhere. What is it? And one thing we're coming back all the time, we get these purple blotches. Doesn't naturally occur. What the heck could it possibly be? Finally, one of our flyers flew near here. There's a purple blob. Couldn't take it anymore. We got in the car, we drove out there. Guess what it was? Feedlot. Turns out cow poop in wet dirt reflects purple. It does. So it drove us crazy trying to program that out. Guess who was interested in the data? The EPA. Fascinating. Because we also make elevation models. Something I'm not going to talk about tonight, but we actually measure the heights of things. And they want to know where all that poop's draining. Right? Because that's what poisons the water supply. So it's my joke to that is, one man's bug is another man's feature. And that's one of the biggest things in all this big data processing. I'm sure you guys find out in your processing. Half the problems you have, pisses off some of the customers and delight the others, depending on what kind of analysis you're doing.
Are you planning on doing any oceanographic survey as well?
No. One of the other, by the way, after the processing is done, that's what it looks like. So that's all the radiometric corrections in there. One of the other things, by the way, I should just go back the other way real quick. I don't know what your politics are in here in Boulder, but if you think there isn't climate change, we can tell you officially, we see it in the imagery. Why you see rows there is there's 24% more atmosphere on the edge of the camera at 9 kilometers swath wide than there is down the middle. We can actually see the haze in the imagery, and we have to program that out. And these we go haze-free days, and that's the effect you get. So believe me, there's might not be climate change, but it ain't good, I can tell you that. So the other one thing, people ask, so what's the hardest thing in processing? Tall buildings? Nope, pretty easy. Mountains? Nope, pretty easy. Water drives us out of our ever-loving mind. Hardest thing to process in this whole thing. Why? If you were to meet at a party and you say what you do, Tom, we're quilters. We take all these images, we sew them together. You tell me when you look at water how to connect the imagery. Right? There's nothing to do it. And the worst part is a moving boat. Right? It's moving a little slowly. We sit there and say, well, okay, we're going to join up. How come I can't reach you? Because you're moving. Sit still. And so if you're out there boating, you see a plane go over, please just stop. So what you're seeing there in the imagery there, this is San Diego. You're seeing spectral reflection is the technical term. And we have algorithms that actually take it out. So, in, out. So how do we do all this? Well, this is our little map reduce thing, and this is some of the features of it. One of the things that when you were coming downstairs today, you happened to be going by the glass wall there, and you saw all really close desks. Microsoft, typical thing, everybody gets an office, and that's where the developers I happen to have 40 developers here that work for me. And but we also do have to have people look at the data before we ship it out. And in particular, some of our new processing, we did a lot of what we call 2D processing or ortho processing. Most of that was manual. So when we did the whole United States and Western Europe, we only had about 20 people up there doing inspection and a little bit of editing. Steep canyons can really drive us crazy if the camera can't see all the way down to the bottom, right? And, it all depends. If the camera didn't see it, we don't see it either, right? And so, but you say, well, but I know there's a canyon there, so we have to go in and fix that stuff by hand in certain instances. So we have folks that do that. So in our graph, unlike MapReduce and Hadoop, we actually have manual operators that can be executing a function in the graph. So we'll get to a certain point in the graph and just sit there and say, you know, the worker bee's upstairs, take an item off of it, do their work, put something back. Sometimes it's just literally a QC step where all they're putting back is good, right? Sucks, right, in simple terms. But other things, when we're doing the sewing together, what we do is we can move seam lines because we have a high degree of overlap in the imagery, and we actually move where we're going to do the cutting, not unlike a seamstress would do and where to put a hemline in an outfit or something like that. So it's remarkably the same idea, right? We learn to cross roads right where we have an even break and not along the edge of it where you suddenly see highways get narrow. A very common error both in Google's product and ours, because we cheat, is we'll be out there somewhere in remote area and there'll be 2-lane road. It'll suddenly become 1 lane, we'll be back to 2. There's a little seam error, right? We just, screw it, can't quite tell, right? So if you actually drove that road, you wouldn't know. So, but anyway, we looked at these other different systems, and so this is kind of the features we have and how they're relative to it. And ones I put in bold were the ones that were a little different than what the other products have. And in our case, we're quilters. We update a mosaic. So when we update that mosaic, one of the features we wanted to have was the ability to say after a job ran to go, never mind, roll back, take it out, put the old quilt back, right? And we'll do that. One of the typical problems, one of our people attending the night, one of the guys who used to work with us, every once in a while, bird poops on the car, right? Don't see it, and drive all day and then go, oh no, bird poop, right? Just as I get told that, we see some splotchy imagery, we want to take it all out and remove it from the processing. We use a directed graph, a little bit more complicated than the typical map reduce and then chaining those together. So you can have any number of items be in a process. The steps are just placeholders for different programs that are going to run. You're going to have n of those programs run, including 0, right? So you might run 1,000-step B1s, 500-step B2s. Our system's a little bit different in that what we do is we have a programmable planner. Instead of you doing key value pairs, you literally make up, I want this program to do that data, I want that program to do this data, and I want these two, another program downstream to take their output and do whatever. So we basically have programmable scheduling, is that how ours works. We actually do use Visio to kind of put circles and arrows together to actually do the routing. Circles means it's a completely automated program that runs out in the containers in Longmont. If you see something that's square up there, it means a manual intervention is taken off a queue, right? Usually you see things square at the end. I'm sorry, not square. The bolded lines means something is going to run manually. It's going to run on an operator's desk upstairs. So typically what we do is we'll take a little QC step at the end to actually sit there and say, hey, this is what, is this good or not, and pass it on. And we actually have a little, what we call our operator console. You can actually see the graph done out linearly as to whether or not it's run. You'll see little numbers up there. They're the number of tasks that were actually scheduled for certain steps in the whole processing. The times on the right are how long the overall step ran until it goes on to the next one. And that is the whole morass that we did up until last year. We have another whole new thing because we are working on 3D now. We are doing some other work with our street side camera system. So we have a whole new one. It just is so big, I can't get it on a PowerPoint slide, right? And it's also changing fairly fast before us. The biggest challenges in doing anything with 3D is actually measuring the heights of things and getting that very accurate. And basically we're considered, our research team in Graz wins the annual, in the photogrammetry community, there's an annual automated elevation processing, and they win it every year. But even so, it's still too crude to do perfect 3D processing. And that's where we are at, Apple's at, Google's at. We actually all know each other on the technical side, and sometimes we whisper in each other's ears, sharing notes. So I mentioned we have our compute site out in Longmont. We actually use the same kind of computers that the Azure guys do. We actually use the same one called SKU from Dell. We just pump them up with extra storage on them. Thing we're pretty proud about, everybody likes to say Microsoft's so rich, blah, 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 blah. Well, the mapping side, I can tell you that all three companies are all poor. We'd rather throw money into imagery acquisition than into computers, because there's no return on that, right? So we wanted to go for the highest power efficiency there is. At 1.03, we're currently the record holder. We may not be any longer. We were a year and a half ago when we set the record at 1.03, but we all play leapfrog in this whole thing. We know, I'm sure the Google guys made a lot of progress because they are very good at what they do in their data centers. Facebook as well. But anyway, 1.0, what that means, by the way, if you're not familiar with the term, is it's a measure of how much your power goes to non-IT. So perfect score would be 1.00. It means only power is going to computers and networking equipment, and nothing to air conditioning or toilets flushing or anything like that. So at 0.03, that's a very, very low percentage. You figure about a decade and a half ago, the typical data center would be 2 to 3. So it'd be way inefficient on there. Well, I said enough about that. The one last thing is, I mentioned we're currently at 72 petabytes. We just took delivery of 2 more containers yesterday. I was actually going to show a little video, but I'm already over time, of them being lowered into place. I'll show you an example of that. We're taking on 60 petabytes this week. We'll get it all spun up by September, and we'll be at close to 135 petabytes, and we get another 30 petabytes in December. So that's an idea big. This is an example of what they do showing up. A novel thing. There's a guy. I don't know what they're paying him, but it ain't enough. He actually walks that baby in there. And I want to tell you something. Those straps are creaking, right? Because that container has 440 servers in it with 40 terabytes each on them. So there's 20 disk drives, and he doesn't have many fingers. He only has about total of about 6 or 7 fingers. He's missing fingers on both hands, and he's dragging that baby in. There's cable snap, and they snap off their fingers all the time. So there's your college education at work. But the big thing is there's no air conditioning. We do everything with swamp coolers. So there's actually vents on the side. They actually blow. At this time of year, the water's going through, so the air is cooled as it comes through. There's no fans on the computers. It's actually just sucked through by big fans. So we got rid of fans on all things and comes out the top. In the wintertime, we actually circulate the heat coming back. I used to joke, our most compute-intensive pipelines when we're drawing the vector maps and we turn them into rasters. And when it gets really cold, 10, 20 below, we fire up the vector pipeline just to keep the machines warm. So, and that's an example of what they actually look like on the inside. So the compute rack is identical to what Wenming is going to talk about when you're in an Azure cloud, what you're actually running on. They're much more balanced in terms of I/O to compute. Imagery is very big, very large. You don't go after it as much as intensely as you do with typical either click-through data or anything off the web or financial data. So we're skewed towards storage in our particular thing. We're pretty proud. We run the computers hot. That's an average compute rate of 50%, measured 24 hours a day, 7 days a week. Why you see those little drop-offs is we have a tough time keeping things busy on Sundays. We queue up enough work, and people leave by Friday, and it all gets done usually on Saturday, and the machines get the loaf. Used to piss off our general manager to no end, and be just after our butts. They try to keep them busy on Sundays. But typical thing, we send out an email. You just see some numbers across. This is pretty typical, where we generate roughly 100 terabytes of new data a day. This doesn't count this counts what we ingest as well, coming off of either flyers or cars. We send this piece of mail out every day. And just to give you some big numbers, these are old numbers. I'm sorry, the capacity is current numbers before we added these new machines. We're not turned on yet. And then some of the other ones are just happen to be some big numbers. So our biggest week was creating 4 petabytes in a week, to give you an idea. So typical thing is we see, when we're humming and we're in peak flying season, 10 terabytes an hour is pretty average for us, right? Things will dry up, and we'll move the cars somewhere, and we'll have slow weeks or something of that nature. So not unlike farming. You know, when the data's coming in, we're real busy. We always take time in December to do maintenance, and because there's nowhere to fly typically. I mean, we flew Australia this year, but there's only 10 cities to fly in Australia. So, whoop, oh, done now. I'm not going to go back next year, so we know we're going to have the winter off this year. So when we got done finishing the United States, we did do Boulder, the last little stretch of Boulder. Interestingly enough, we had our camera guys here for the camera summit. The guy that flew this came in. And just to give you an idea of some of the challenges, our joke is it's an outdoor sport, and we have to deal with, we have to deal with weather, we have to deal with legal. We had people in Louisiana driving our cars off the road, stupid idiot. We got taking pictures of them. We just went down to the sheriff's office. We said, "Here's his pictures." "Oh yeah, that's Earl. I know Earl." We picked up Earl, arrested him, right? But anyway, we had chalk artists from Denver come up, paint on the garage right next door to us. And we all laid around it. And the funny part is, that same day we had picked months in advance was the day Michelle Obama came last year to speak at CU and grounded our airplane. So there we are, post a thunderstorm that day. We got chalk, we got $3,000 worth of chalk art outside. We got the rain tiles coming, can't fly with it. And we go, oh no. And luckily enough, we got clearance to fly. Because they have an F, when she's here or he's here, there's an F-16 flying around. And you don't belong there, you won't be there long. So thank you very much. I went on a little bit too long. Thank you for coming. I hope you enjoy the rest of when you install.